exam. I believe the way the stats worked out, the average was a 62 and the median was a 76. Now, what is this indicative of? Well, 4 people did not take the exam out of 24 people, which means we have some potential outliers, which means would we trust the mean or the median more? Probably the median. That's just, I would be more likely to use the median as a form of central tendency. So the expected value for this exam would be considered a 76, then the 62 would be skewed by outliers. Additionally, I have the grades posted in my math lab. So your grade is already recalculated in there based off of the midterm, or not the midterm, the first exam. So currently, the way my math lab is determining your grade at the moment, it only has 3 assignments to work with: your homework, your quizzes, and your first exam, which means so far they are all weighted as 33.3% of your grade at the moment. This will change as you take the other 2 exams and as you do more homework and quiz assignments. But I wanted to give you a heads up about the derivation of the grade. Additionally, if you want to see your exam, so I'm picking these exams back up at the end of class if I handed them out to you. So, but we can talk about your exam. If you want to talk about any specifics of your exam, or if you think I made a mistake, you could schedule office hours with me. Just shoot me an email and say, hey, I don't think this is right, or hey, can we talk about this? I thought I got this one right, or why did I get this one wrong? We can talk about it then. If you want to see your grade, so if you're virtual and want to see your grade, if you're virtual and want to see your grade, then you either got to come to class. I'll bring the tests as well on Wednesday, and you can look at them then. Or again, you could just schedule an office hour with me, and I can show you your grade and show you what you got right or wrong in that regard. But besides for all the exam stuff, I additionally noticed an alarming number of people did not attempt the homework on the least squares regression. And additionally, there were 12 out of 24 people who missed last Wednesday's class period. This is not a very good number. And of course, as you know, the consequence for that, you don't get the lecture for the class, which means although I did move least squares regression back to tonight to do, you didn't attend class and you didn't give me an excuse for that class, you're going to have to figure it out on your own. So you'll have to figure this out or ask a classmate. But you have to come to class. The comparisons are very clear how coming to class benefits your grade in just any subject. It's clear in any subject. COVID-19 has made this correlation especially clear. Again, I only emphasize this as I want you all to build good habits for your future semesters here at Southeastern. We were all thrown into a very unfortunate circumstance with this COVID stuff, and it builds very bad habits. I only say this out of concern. But besides for that, I did establish the next 3 due dates. So again, I'm giving you one more night to do least squares regression if you may not have done it, or if your grade was not a 100%. If you have any questions on this stuff, you can ask me. I don't get too many emails from this class. You can always use the easiest way to ask me about a question is use the Ask My Instructor thing here. The only thing I ask is whenever you do this, just tell me what you've tried. Normally I respond with, what have you tried? I'm happy to help with these questions. Or if you need to schedule office hours, that's fine as well. I'm willing to help as much as I can. So keep all that in mind. So again, least squares regression, do tonight if you didn't do it, or if you want to get your grade a little bit better. Probability rules, we almost finished it last Wednesday. We're going to finish it today. We only have one more question. That'll be due Wednesday. That should be a fairly quick section right there. And then mainly the quiz as well will be due Friday. And we'll finish discrete random variables today. And whatever time we have remaining, if any, we will talk about the first exam. So the 3 assignments due, and I graded the first exam. Are there any questions or anything I may have missed before I proceed with the new material? If not, let's go ahead and get started. So we were on the section on probability, and with this section, we were talking about events, sample spaces, and probability. Mainly an event is some specific outcome, such as if you flip a coin a bunch of times, a specific event might just be landing on heads a certain number of times. It's a specific outcome. In the sample space, we talked about that as being the space of all the possible outcomes. So if we're talking about flipping a coin, then the number of combinations, or the different combinations that we could get, you can get a bunch of heads, or a bunch of heads and one tails, or some heads and some tails. All those combinations would be part of the sample space. So this was some of the terminology we established, and we did mention this before. I know I wrote this down last time, but we use these curly braces to represent the collection of different outcomes. So if it's asking for the sample space, in this situation here, where there's 2 fair dice, and you're considering the sum of the dice, well, we have, really it's 11 options, 2 to 12. And those dots just mean continue in this fashion. So 2, 3, 4, dot, 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 of course, means just fill in the blanks, or the blanks should be cleared to fill in from there. And we wanted to determine the probability of rolling a 6. So when we were talking about probability, we were sort of, in some sense, we were approximating it. And again, if you took 105 last semester, you should remember this problem very well. But we approximated this probability by determining how many occurrences can we have, and what are the total number of outcomes. Now, when we roll a 6, well, in our sample space, a 6 is one of the 11 numbers. So some people may be inclined to think that the probability is 1 over 11. But that's not true. Because there's not simply 11 different combinations. There's 36, which the problem tells us. Which means out of those 36 combinations of rolling maybe a 1 for the first dice, a 1 for the second dice, a 3 for the first dice, a 4 for the second dice, all those combinations, how many of those will result in a sum of 6? What we were talking about before was, well, we could roll a 5 and a 1. So a 5 for the first dice and a 1 for the second one. 4 and 2. 3 and 3. Just wrote that one. A 2 and a 4. 1 and a 5. And those would be the total number of combinations. So it's a counting game, in other words. And with that, there's 5 options. So there's 5 ways in which this can happen. and we divided that, or we will divide that by the total number of options, which was 36. So the 5 being how many times can the specific event occur, and the 36 represents the total number of outcomes. And generally, we've been expressing all of our answers as proportions, as decimals. So very quick computation in the calculator. I'll go ahead and pull up momentarily here. Call it 0.1389. So we would say that this is the probability. And then part C, if you have the notes printed out, I don't know what, the second blank was going to be for the word about, but I already put it there accidentally. So kind of to explain why I would have a blank for the word about, if you see this in the probability homework for part C, for example, they will give you 2 answer choices for this following prompt. And one of the answer choices says the word about, and the other one says exactly. Now, if we look at the context of the problem, if the 2 dice are rolled 1,000 times, we're ultimately trying to interpret the results of part B. So we would try to interpret, would about a certain amount result in a 6 out of these 1,000, or would it be exactly? And normally with probability, it's an approximate amount. That's why I have the word about underlined. It's to distinguish from the word exactly. So if you see the word exactly in the homework for probability, that one cannot be correct, as probabilities do not state things exactly. It's a good approximation. We talked about this from the law of large numbers that we talked about this past Wednesday. So if we roll these 2 dice 1,000 times, then it is expected that about how many of those would result in a 6? Does anyone have any idea of how to extrapolate this information? Roll a dice 1,000 times, there's a 0.1389 chance of that occurring. How do we put those 2 numbers together? Well, I'm going to spoil the fun. Roll the dice 1,000 times. The proportion tells us ultimately what percentage of this will give us the sum of 6, which we found in the last part. So that's a pretty quick computation. 138.9. Which makes sense. We move the decimal place over 3 to the right by multiplying by 1,000. So this tells us the proportion that we would be able to expect. That's one way in which probability helps us, is that it allows us to scale up to a certain number of trials. Now, the problem is, this isn't going to be the final answer because, well, dice rolls are a discrete thing. As in the number of outcomes, you can't really have 138.9 outcomes to become 6. It has to be a whole number. I'm going to round this up to 139. Because again, dice rolls are a discrete outcome. or as we'll learn later, a discrete variable. And then we can go on to find the probability that the sum is an even number. So remember, even numbers, well, technically 0 is 1, but it's not in our sample space. So 2, 4, 6, 8, 10, and 12. So there's quite a number of combinations we can get from that. And instead of writing all of them out, because there's going to be a lot, so let's just go ahead and look up the look up one of these images. So we can just simply look on here and find all of the dice outcomes that's whose sum is an even number. Here's 2. These ones are 4. These ones are 6. 8. And this, you might be familiar with this diagram from 105. There's 10, and there's 12. All we have to do is count all of those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18. That's pretty much it. We count all the occurrences. There are 18 dice combinations whose sum is an even number. So there were 18. Another way in which this would have helped, this is half. 1/2's even, 1/2's odd. And 18 divided by 36, as you might imagine, just a half. That was another way you could have figured it out. There's a lot of symmetry with dice rules. So this would be the probability, 0.5, which corresponds to 50%, or half of the sums will be even. Of course, that means the other half will be odd, which makes a little bit of sense intuitively. And so let's see if you can all redeem yourselves. The 2 dice are rolled 100 times. It's expected that about how many of these will result in an even number? That's 50. And the reason why it's 50, just like in part C, this is almost exactly like part C. It's 100 times. We know that the proportion is 0.5. Again, that's why it's good to have a proportion as an answer, because it's in a form for which we can apply some arithmetic. Percentages, we normally don't use percentages in computations. We normally convert those to decimals and then use the decimal in computations. Here, that just skips the middleman. And so this computation right here, or what's half of 100, it's 50. And again, it's about. We're using the word about and not exactly because, well, probability doesn't state anything exactly. It gives a strong approximation, though. And the approximation is stronger and stronger the more trials you do, based off of the law of large numbers that we talked about in the last class session. Does anyone have any questions before we move on to the next chapter, which is kind of similar to this section, this chapter here? Right, if not, as I mentioned, this homework shouldn't be too crazy. This homework's due Wednesday. So again, least squares, I brought that one back up because some of you didn't do it. Made that due tonight if you want to redeem your grade. And again, probability rules due Wednesday. with the quiz due on Friday for these past two sections. Okay. Let's move on to something that formalizes the idea of probability from a statistical standpoint called discrete probability distributions. So we've talked about probability and probability models from the previous section. And really, we're going to be redefining all of those things, but from this more technical perspective. We're kind of generalizing the notation and the observation a little bit to get some more information out of what we may be looking for. So in this section, we're looking at something called discrete random variables. And to understand what discrete random variables means, we have to talk about just random variables. What does it mean to be a random variable? It's a numerical measure of the outcome of a probability event, or a probability experiment, rather. Numerical measure of the outcome of a probability experiment. And its value is determined by chance, hence the randomness. And additionally, we use capital letters to denote these variables, these random variables. We use capital letters. X is the most common one. That's the one that's generally defaulted to, but sometimes we'll use an intuitive variable, like T for time, but X is the default variable. And you might be wondering what all of this refers to. I think the best way to define it is to just take the most simple probability example and just start mixing and matching what certain things refer to. In example one, I sort of described two scenarios where we could think about random variables. So if we think about an experiment, so I'm using the wording of experiment to represent what we are trying to determine, trying to figure out the outcomes and probabilities for flipping two coins. So very simple thing. You can visualize flipping two coins in your head. So I listed all of the outcomes here. So of course you could get both heads and tails, and so on and so forth. Instead of looking at the probability of just one of these outcomes, such as what is the probability of getting heads one time, we could count and see that that's 2 out of 4. We can instead just implement a random variable. So that's where the random variable comes into play. Could represent the number of heads of the experiment. So you notice, rather than a specific outcome. So instead of forcing ourselves to look at a specific outcome, we can use a variable to represent the total scope of outcomes. So notice how we're basically using a variable to describe a sample space. That's what we're doing here. It's a variable used to describe a sample space. So that's where this generalization comes into play. And so notice how the capital X, that is the random variable. So just trying to tie the terminology in a little bit. So capital X represents the random variable. And this would be the number of heads, because again, the random variable refers to the total collection of options for some event. And then there's this one little thing at the end. So if we flip a coin 2 times, 1, 2, we're letting capital X be the random variable that represents the number of heads that we get. Now in our 2 coin example, we can either get no heads, 1, or 2. And notice that is exactly what is characterized at the very end here with a lowercase x. the capital X refers to the sample space, in other words, and the lowercase x refers to the specific options that we could have. So this is sort of how this notation comes into play. The capital X refers to all the options. The lowercase x refers to the specific options. And again, this is a way to generalize our interpretations of what's going on. Another example. Well, we can measure the time between the arrivals of cars at a drive-through. Now, in this case, we're looking at time instead of, well, the number of heads. So there is an inherent difference with between these two values that we're looking at, these two variables, in other words. Notice, to not be confusing, we use a capital T just for time, just so we don't use X again. And since we're dealing with time, notice that I'm not using an equal sign like I did in the previous problem, because time is, and there's a word for it, a word I'm looking for. Let's see if anyone can figure it out. It's continuous. Time is continuous. The number of heads you get is discrete. And because of this continuity of time, we're using a lowercase t to complement the uppercase t. So we're just saying t is greater than 0. It's not equal to 0, equal to 1, equal to 2, because within this amount of time, you can have even smaller seconds. Time is continuous. That's why we're using an inequality. Now, there's, I think, 1 or 2 homework questions that might ask to determine whether a given variable is discrete or continuous, which is based primarily off of this notion of determining, or the thing you are looking for, or the variable you are given, is that a discrete variable or a continuous variable. It's very similar, in fact, almost exactly the same as what we did in, well, the first exam. But a discrete random variable, again, this definition is very similar to the one we talked about in the very beginning of this class. It's either finite or countable. A continuous random variable is infinite and uncountable. I wouldn't imagine anyone uses the book in this class. If you do, their definition of a continuous random variable, I believe, is incorrect. They did not emphasize that part, which definitely makes it a more accurate statement for reasons that are very logic-based. Kind of interesting. So, of course, in example 1, the coin flip problem would be an example of a discrete random variable, because the coin flips really don't go into decimals. You either get 0 heads, 1, or 2 heads, as opposed to time, where there could be particular decimals between the times. They don't have to be just positive whole numbers. And just to sort of see this again, we could look at example 2 down here. In case any of you are still writing the definition, I'll do this for now. Determine whether each random variable is discrete or continuous. State the possible values of the random variable. The speed of a car captured by a radar gun. All right, so would this be discrete or continuous? I ask you all this. Is this discrete or continuous? This will be continuous. Things like speed distance and time are continuous variables, temperature as well. This would be continuous because of speed. And then they also want us to determine the values of the random variable. Now we could use S for speed. I'm just going to use a capital X. I think that's what the homework the homework uses online. So the question is, what values of X can we have? And so I guess in particular, I should write values of X. And then we're going to use a little x, so that's a lowercase x, to sort of compare this to any potential values we can have. So speed, well, we know speed's a positive value, so we're not looking at negatives. But does speed, well, since speed is continuous, we don't necessarily use an equal sign because that means we might be dancing around decimal values. So instead, this is greater than 0, or it could be greater than or equal to 0. Depends. I don't think a radar gun's going to be concerned with cars that are not moving at all. You're just going to say greater than 0. So just any speed that's greater than 0. Those are all the possible options. So this would be the sample space. These are the total number of options for the radar gun to catch. Of course, I mean, the radar gun may have a limit, because normally what it does is sends out a laser or some sort of, it sends out some sort of laser that hits the object, returns back, sends out another laser at a certain millisecond or fraction of a second, that comes back. The displacement between those two lasers in relation to the object will compute a miles per hour. Pretty interesting thing, but there are certain limitations. But we won't worry about that either. More so food for thought. The number of students in a Math 241 class with 24 students, so that is this class, that took Math 105 last semester. That could be a discrete random variable. So would this be, well, I just said discrete, so I already gave that one away on accident. It's discrete because number of people, that's a countable and finite thing. Discrete refers to really just people in general. Generally, when we refer to people, that's a discrete variable. And so the values of x, now what would these be? Anything, we're using a lowercase x.
24.
Well, remember the values of x are going to be any number of students, any possible number of students from the 24. So x could be, what about if no students took 105 last semester? Well, 0 could be an option.
So 0, 1, 2, 3, 4, 5.
Yeah, so all the way up to 24. So we do have a limit here. So basically what we're doing is we're considering, so again, each one of these values of x would represent some event, and the capital X is representing the sample space, in other words. So this section is very closely related to the previous section. It's just pretty much adding variables to it, but nothing computationally or algebraically insane, mainly just to refine all the stuff going on. And so I mentioned down here, we're only going to focus on discrete random variables for this whole chapter. So really we'll just focus on discrete ones. So moving forward, everything in this chapter will be discrete. So Now that we have in other words, the sample space, the discrete random variable, now we're going to move on to assigning probabilities to those. So so basically what we've done, we've listed all the potential outcomes. Now we need to list out the probabilities for those outcomes. And that's what comes down to a probability distribution. And so this is just the possible, well, ultimately what it refers to is the outcomes and their probabilities. That's it. And we use a notation that we're virtually recycling this P of X notation, but the way in which we, I guess, verbalize it is a little bit different now. The probability that the random variable capital X equals lowercase x. It no longer just means the probability of an event like we talked about in the previous section. It's the probability, we treat it the same exact way, but if I use this wording, or if I use this notation, this is the wording I'm referring to throughout this chapter, and probably throughout the next chapter as well. The probability that the random variable capital X equals lowercase x. So it's basically saying, what are the chances of our random variable equaling one of the, I suppose, the number of students who took 105 last semester. And there's two requirements for any probability distribution. They may look kind of weird written below. I mean, there's a capital sigma there for some reason, but I went ahead and just interpreted those off to the side. And you might notice we defined those exact rules in the previous section. We did this in the last section. Here I'm just using some slightly more compact notation. And you might see this notation come up, but all it means is all the probabilities have to be in between 0 and 1 inclusive, so they can be 0 and 1 as well. So we mentioned that in the last section. And sigma just means sum, so it means you add stuff. And so the second rule says the sum of all the probabilities has to equal 1. Or in other words, 100%. So again, these are exactly things we talked about in the previous section. And we're actually going to do an example to, see how well we understand this. Now, example 3, let X represent the number of siblings in a randomly chosen Math 241, or a randomly chosen Math 241 student has. So we did this actually in one of the first, can't remember when we did this, but I asked you all how many siblings you had. And so I just recycled that information. The probabilities over here, so notice X, lowercase x, represents the number of siblings, obviously. And capital P of X, that represents, well, these are the relative frequencies. So remember, that was if we had one student, one student that had 0 siblings, and there were 25 people in total, what does that come out to be? And so just emphasizing where I obtain these values from. So I think before we had one student that had no siblings, and out of 25 students, so you see where I got that from. But you might notice one of these is blank. One of these is blank, and we're going to figure out that unknown value. And I already said that this table is a discrete probability distribution. Now, what that means That's just saying that, well, all the probabilities better be in between 0 and 1. That's between 0 and 1. That's between 0 and 1. That one is, that one is, that one is. So far, so good. So you might already see the remaining axiom that we have to prove. The sum has to be 1. So it's a pretty easy problem for the most part. Well, if the sum has to be 1, then guess what we're going to be doing a lot of? Subtracting. The 0.04 minus the 0.24. So we're basically just subtracting all of these off one at a time. 0.4 minus 0.16 minus 0.12. So let's do that right fast. And we get 0.04. .04. So that's the missing one. And that will make this a probability distribution, or a discrete probability distribution. Discrete because the possible values are finite or countable. They're both. So hopefully that's pretty straightforward. Let's move on to something that might be a little bit more engaged. The mean of a discrete random variable. So to determine the mean of a discrete random variable, there's a formula for it, actually. And the formula may look technical because there's that capital sigma notation again. And there's a few other things going on here. So it doesn't look like a very fun formula. So as I describe this formula, I'm going to describe how to apply it in example 4 here. So basically, for that number of siblings problem that we just talked about above, we're going to determine the mean of this probability distribution. We're going to determine the mean of this. So they're just saying use this u of x, or mu for the Greek letter. They're saying just use that notation no matter what. And what this sigma of x times p of x notation represents, so it actually breaks down really nicely. So we're doing this for the table up here. You multiply the rows together, and you add that to the next multiplication of the rows, and you add that to the next multiplication, and you keep going until you run out. That's all it's asking for you to do. That's what it's asking for. The multiplication in the formula means you multiply the rows and the sigma. So that capital sigma notation means you add whatever the product is. So if I go ahead and zoom this out a bit, so I can look at both, this would be 0.0. Actually, let me start with 0. So we multiply the rows together. 0 times 0.04 plus 1 times 0.24. So again, it's the rows, then we add them to the product of the next row. Plus 2 times 0.4 plus 3 times 0.16 plus 4 times 0.12 plus 5 times the last one that we found, 0.04. And it's calculator work from here. So of course, 0 times 0.04 is going to be 0 plus 1 times 0.0. Oops. 1 times 0.2 times 0.4. 2 times 0.4 plus 3 times 0.16. 4 times 0.2 plus 5 times 0.04. And so the average number of siblings based off of that probability distribution is 2.2. So we expect a random, so let's see, the population, it would be the expected number or the mean number, average number, all the same thing, of a randomly chosen Math 241 student. I would expect you to have 2 siblings. So that would be it. They might or might not have you round this 2.2 because we're dealing with discrete random variables, which means we generally deal with whole numbers. So they might ask you to put in this, or they might ask you to round to a 2. It just depends on the context. Because it wouldn't make sense to say that I expect you to have 2 1/5 siblings. So really the formulas so far should be okay as far as presentation goes. There is one more thing that we need to talk about, which is, of course, the standard deviation. Now that formula looks a lot worse. There's a lot more stuff going on. But with this formula, really the only thing you have to remember about it is the notation, sigma with the subscript of an x. Because we get to do both the mean and the standard deviation in the calculator. So we get to do both of those in the calculator. So naturally, anytime you see a complicated looking formula, just know that the calculator is going to bail you out. So as I say down here, note, going to find it in the calculator. But we already know how to do this in the calculator, I claim. It's on page 29 of the notes. So if we look back to page 29, this was when we dealt with grouped data. It's the same exact process for when we dealt with grouped data. The only difference is that the first column will be the possible discrete values, and the second column will represent the probabilities. This was something that a lot of people forgot about on the test. I think out of 50 students I have in both of my sections combined, I think maybe 10 of you did this correctly for that one problem on the first exam. So let's make sure we can all do this now, which I'll do it for the upcoming problem. So we all make sure we know how to do it in the calculator. All right, so this is where I'm going to ask all of you questions. The number of televisions, I'll just have you raise your hand. So I'm going to ask how many of you, and let's see, well, let's see how well the data spreads, and then I'll see if I need virtual's help for this. So in class, raise your hand if your household has 0 televisions in it. So I guess I'm the only one. 1, 2, 3, 4 or more. 1, 2, 3, 4, 5, 6. Let's see. 7, 8, 9, 10, 11. I think I can make that work. Okay. So notice with this, I'm going to go ahead and fill out a discrete probability distribution table. As you can see here, and the probabilities are going to be the relative frequencies. So I'm the only one that doesn't own a TV. Haven't owned one in a long time. It's 1 out of how many people we surveyed in total? 6, 7, 8, 9, 10, 11. 1 out of 11. .09. Of course, the next one's easy because no one has just one television in their household. Next two are going to be the same computation. And 6 out of 11. Actually, just to make sure that the sums add up to 1, I'm just going to subtract 1 to make sure. So let me do this on my screen. Just to make sure all the sums of the probabilities add up to 1, I'm going to just do 1 minus 0.09 minus 0. We can skip 0.18 minus 0.18. Which I think that would have been the same thing regardless. But now we know that the second column is going to add up to 1, which would have worked out anyways, but rounding always makes things sometimes ambiguous. So here are the distributions from this. Okay, so with these distributions, I'll go ahead and try to leave that on the screen as I go ahead and construct a graph for the discrete probability distribution. Now this graph for a discrete probability distribution is not going to be a histogram because for whatever reason they use a different notation for this. They use this notation where the line goes up to a dot. So if anything, let me just place all the dots. So 0.18 would be the next one. Be about right here, and then right here. And then for 4, it would be, well, I didn't expect any of these to be over 50%. But it'd be up here then. I guess a little bit to the left. Maybe right here. And then you just draw lines going straight down. And in fact, I'll use a different color to emphasize that there is a point, and then there's a line that connects to that point. So that's what they use, but it's really the same idea as a histogram, except instead of boxes, we have these weird-looking symbols. Just a line of points. So we're going to go ahead and figure out the mean and the standard deviation of the values we just found. So the way we're going to do this in the calculator, we're going to need the table. In the first column, in the 4 or more, I'm just calling that 4. Again, that's normally determined in a statistical study. They'll normally just clump any excess values into the highest value. They do that a lot of times for what could be outliers. So we're going to go up to 4. And then in the second column, we simply put the relative frequencies that we found. This process is used really any time that you have 2 data sets, or maybe not data sets, but 2 lists of information that correspond to one another. Now, I think everyone did this correctly for that one exam problem. So if you have your test, if you don't, you can't really look, but it was problem 4 on page 5. that said use class midpoints. It was the same process for that, and almost everyone did it the not correct way. I'm going to explain how I think you messed up on that. Because everyone put, I think, 97.2, which is not correct. So what you have to do, what you would have done for that problem, and what you also do for this one, is when you go to stat and one variable statistics, on my calculator, it's going to look different. See, if you just press enter, it's not going to work. One variable statistics will only take the first column by default. So we have to tell it. So I'm going to press second and press just 1 on this calculator. I'll explain the 84 ones or the other ones in a second. So if you have this one, it's L1, then you have to press the comma button right here above the 7, and then second and 2. And again, this process is highlighted word for word on page 29 of the notes. So please go to that page for a reference, a step-by-step reference. And this will give us the true average that weights the probabilities. That's what we need. The probabilities also weigh everything. So really what we have is that the mean, actually, sorry, not that. The notation they use is mu of x, that's 3.1. And I'll go ahead and put the standard deviation. .24. And notice I'm using the sigma 1. I'm using the sigma notation. Because that's why I mentioned to remember that notation up here. Using the sigma 1. Now, if you have one of the fancier calculators, you have to put L2 next to where it says FREQ list. That might have been your problem from when you were taking this exam. So I would expect if I go to a random 241 student, I would expect them to have, on average, 3 televisions in their household. Now, this may be just from a statistical standpoint, from just the premise of the study, this might be skewed because I took the number of televisions greater than 4 and I just morphed them to 4. I mean, does anyone in here have a household who has 7 or more televisions? So that would be considered an extreme value, but in an age where televisions normally appear in every room that's not the kitchen, or I would imagine not the bathroom, but I don't know. Does anyone have any questions about this one before we look at one more? If not, there is a sort of an application problem here that involves, well, the game of roulette. I don't know if you all are familiar with the game of roulette, but it's a giant wheel. So it's a giant wheel like this. Generally, a metal ball is dropped, and the wheel is spinning around, and the metal ball will stop at one of these random numbers, and you can bet on what number or what color or what, whether it's even or odd. You can bet on whether it lands on numbers 1 through 12. There's a lot of different probability options. So this game is completely luck-based. So, but if you bet on something that's really hard to occur and you're actually correct on your guess, it'll give you a lot more money than if you just guess on if it lands on a red or a black number. So there's a lot of probability to it. And in fact, casinos make a big deal about determining how much they would pay you for a certain, I suppose, event occurring. So let's just say in this game of roulette, someone places a very safe bet of $5 on just the number 17. So just the number 17. And I already wrote down, instead of wondering what the probability is, let's say that there's a 0.026 chance of that number being landed on. 0.026, that's a 2.6% chance of your number being landed on. If the ball lands on 17, the player wins $175. If it doesn't, well, then the player just loses $5. What's the expected value? And by expected value, that just means the average or the mean of the game relative to the casino. Because we can look at this problem relative to the player, but we're going to look at it instead of relative to the casino. So with the casino, so really what we can do is think about this in terms of probability. Now, if anything, we're going to have a win row and a lose row. And we kind of need to figure out what all of these refer to. These are things that casino, at the end of the day, they want your money. Slot machines are rigged to only allow a certain number of wins after a certain number of pools. It's all probability based. If any of you ever went to the bowling alley here in Hammond, you might remember that game where the light goes around the circle, and if you stop it right in the middle of the two arches, you win a bunch of tickets. And I played that game a lot as a kid. And then I realized the game is incredibly rigged because it will only stop there one out of every mini attempt. There's a YouTuber named Mark Rober who talks about it in great detail. But anyways, we know the probabilities already. So we can go ahead and put those in already. So what is the probability that the casino is going to win? See if anyone can get this one.
0.974.
It's 0.974. Yes, exactly. 0.974, because there's a 0.026 chance that the player is going to win, who is not the casino. So you have to subtract 1 minus 0.026 to figure out the chances of the casino winning. So they have very high odds here. And if they win, they get $5. But if they lose, you might think, all right, if they lose, then they lose $175. Not exactly true. The guy bet $5, and he's going to, so you get $5 as the casino because the guy pays to play, and then you have to give him $175, which means you're losing $170. So that's how much the casino loses, because he's paying you $5 to play, and then you're turning around and giving him $175 after he wins, if he does win. And then from here, the final thing we have to do, well, we already filled out the table. I wish I left a little bit more room. I guess I'll write it down here. The expected value is just the mean. You could do it in the calculator. There's only 2 rows, so we could just do it by hand. 5 times 0.974 plus negative 170 times 0.026 . Five times 0.974, really it's minus 170 times 0.026. And I get 0.45. What this is saying is that on average, the casino is expected to make 45 cents off of the player. Of course, this number is very low because they're only betting $5. But when you think about hundreds and hundreds of people showing up to your casino, then this value is going to get larger and larger. Because out of every 100 people, you would imagine that 1 or 2 people will actually get this correct. So these are certain things that casinos consider in order to figure out, all right, how much should the odds be, and how much money are we going to get from this? Is this even a profitable game to play? Does anyone have any questions about this? Because if not, I'm expecting this homework on discrete variables to be due next Monday, so you have a whole week to work on it. And besides for that, I want to go over the first exam. I want to go over that because there are some places that people messed up at that I want to yell at you for. Probably small little mistakes,